So putting all the physics together, we can divide the world up into different size regimes. These are different rough sizes where different bits of physics apply. Now, the laws of physics apply to all scales, every law of physics, and the boundaries are not hard and fast. This is simply a guideline for what sort of physics are probably going to be most important for typical things travelling at those sort of sizes. So we start off with the normal world. This is the world of our day-to-day experience, sizes millimeters up to kilometers, and we kind of know how that works. So when we get a bit smaller, as we've just seen, we're down in what I like to call the micro world. And here we've seen that gravity is irrelevant, mostly. Friction and drag dominate. The Reynolds numbers that we talked about elsewhere in the course mean that everything is very laminar, whereas up here in the normal world flows are usually turbulent. Everything has a very large surface area compared to its volume, so things tend to be in thermal equilibrium. So this, if you like, is the world of dust grains and pollen, mosquitoes and bacteria, and they live in a very different world from us. This being the world of elephants and cats and people. When you go smaller still, you're going into what I would call maybe the nano world. Now in this case, what dominates is random thermal motions. This is the one we're going to talk about in the rest of this lesson. So all the atoms are jiggling about because of heat, and on this sort of scale, those jiggling motions, atoms bouncing off other atoms, completely dominate. So this is the world of nanotechnology, and it's even weirder than the micro world. On even smaller scales, we're on the quantum world. Here, we have to take into account the fact that matter is actually waves, because the wavelengths are of this size typically. So this world, things can be in two places at once, everything's a probability wave, electron can interfere with itself, and all sorts of quantum weirdness goes on. So quite different. How about going up to bigger scales? Well, when we're up somewhere around here, we're in astronomy world. On these sort of scales, gravity dominates, gravity and momentum. Drag is irrelevant. And things tend to move in nice orbits, endlessly, never slowing down. And there's actually an even bigger regime, up beyond about 10 to the 22 meters, so off the scale here, which would be a cosmology world. On these really big scales, tens of millions of light years and above, it turns out even gravity starts to become fairly unimportant, and everything is dominated by dark energy and by the expansion of space-time, so relativistic effects. And there may well be some more worlds down here below the quantum world, and so there's grand unified theory and things like that. So the point here is that there are many laws of physics and they all apply at all scales, but which one dominates tends to depend a lot on the scale. So you wouldn't worry about gravity down here, you don't really worry about quantum diffraction up there, usually. There are exceptions to all these things, but this gives you a good first guess as to what are going to be the most important physical principles on some different scale.